Hello everybody, and welcome to the 6th video in the TypeScript WebGL tutorial series. So, if you recall, last time where we left off was we added a uniform to allow us to draw this triangle in different colors. So what we're going to do today is we're actually going to formalize some of this stuff and set ourselves up with a sprite rendering system. And so to do that, what we're going to have to do is, again, abstract some of the code that we already have in place and extend some of the things that we have to actually encapsulate some of this logic into a new sprite object. So right now in our engine class, we've got all kinds of things that the engine itself shouldn't be concerned with. So we've got a shader here, we've got a GL buffer, and we're doing all sorts of things in here, like we are setting uniforms and we're setting all these position attributes, or we're setting this attribute rather, and we're loading up our vertices and all this different stuff. So we're going to be able to take some of this stuff out of this class and put it into a sprite class. So before we do that, the first thing I want to do, actually before we move anything, is I want to adjust our vertices a little bit. So right now what we've got is we're rendering a triangle, and we only have 3 vertices at the moment, which gives us 1 triangle. And if you've ever used a game engine, a sprite is basically a quad, which means 4 points. And what we need for a quad is we need the ability to basically draw two triangles, because WebGL, for the most part, only really deals with triangles. You always want to think of everything in triangles. So even if you've got a complex shape, ultimately it's made up of triangles. And so we need to convert our example to use triangles instead. And there's some work that we have to do to actually get that to function properly. So that's the first thing that we're going to go ahead and knock out now. So the first thing I want to do is I want to add some more points to this, because 3 points obviously isn't enough. But because, like I said, we actually need to draw 2 triangles to make up our quad, we actually need to add 3 more points. So in our example before, we have the first point, the second point, the third point, and now what we need to do is we need to add a 4th point that's different from these, but 2 of these points are going to wind up being reused. And so what I'm actually going to do is I'm going to start our second point off using the same vertex information as the third point. Oops, I forgot a comma there. And so what this is going to do is this is going to tell WebGL, okay, I want to actually start our next triangle at the exact same point as the last point on our previous triangle. And the next point is going to be at this location. And this is our new location. So if I go back here to Paint and I draw my crappy little graphic here that I had before, right? So this point is 0, 0, and then this point is 0, 0.5, and then we have 0.5, 0.5. What we need is this point here to actually give us our 4th point. So these are our first 3 points, and our second 3 points is going to start exactly at this place, come down here, go over here, and then it's going to loop back to here. So our first point is here, which is the same one as this guy here. And the second one is going to be down here, so it's going to be 0.5, 0. And our last point is again going to be 0, 0, 0. So I'm just going to copy that line there. And the other thing I'm going to do, well, actually, let's go ahead and just test that really quickly. Okay, so now I've got my 3 points here, And I'm going to go ahead and run this. And now we have our quad. So it's not a whole lot of fanciness that we have going on here. Obviously it's still orange, it's still very boring, but at least now we have a quad that we can use for our sprite. So that's great. The next thing that we need to do is we need to go ahead and move all of this to its own class. So that's what I'm going to do now, and we're going to call this class sprite. So in the graphics folder, we want to right click that. We want to add a new TypeScript file, and we'll call it sprite. And we'll set our namespace to TSE. And we want to export class sprite. Okay, and we want a public constructor, and we want to always take in a name, so we'll start with a name, which is going to be a string. And we'll go ahead and take in a width, which is going to be a number, and a height, which is also going to be a number. And I think that's going to be it for right now. You know what? Let's go ahead and set some defaults on this width and height too. Let's go ahead and set these to have a default value of 10. So that just makes things a little bit simpler when we actually call the constructor. So all we'll really have to do is pass it a name, and if we don't pass anything for width and height, it'll just use 10 by default for those things. The other thing we're going to need to do is a couple private variables. So we want a private width number, private height number, and of course our private name string. And we want to just copy those values over to our private members. So this dot name equals name, this dot width equals width, and this dot height equals height. Great. So the next thing we're going to need to do is start pulling logic out of our engine and putting it into our sprite class. So the first thing that we want to move is obviously this GL buffer. So I'm going to cut that and paste it into our sprite class. And that's going to remain a private for now. And let's close out some of these other files actually. We don't need some of these things. Okay. And the next thing we're going to do is we're actually going to create a couple more methods in our sprite class. So we want to create a public load, and that's going to be a void return type. We want to create a public update, and we want to create a we want it to take in a parameter called time, and that's going to be a number. Whoops. And I'll come back to that in a bit. It's going to have a return type of void also. And let's also create a method called render. Let's call it draw actually. And that's going to be return type void as well. Okay. So back over in the engine, we have some errors that have popped up here because we've removed the buffer out of this class, and that's fine. So the first thing that we want to do is actually we want to go into this create buffer method, and we want to take everything that is in that method and cut it and paste it into our load method in our sprite class. And I don't believe we're going to get any errors there. Ah, yes we are. Okay, so let's see. So what we're actually going to do, you know what, we'll come back to this. Alright, so we can actually get rid of this create buffer class in the engine. I'm sorry, the create buffer method in the engine. Let's go ahead and get rid of that. In the loop, we want to cut out these two calls, this buffer.bind and buffer.draw. And we want to put those in our sprites draw method. And I believe that actually takes care of the modifications that we need to make in the engine for right now. We're going to be coming back to this and adding some things here, but okay, so now we have a bit of a conundrum because our position attribute location requires that we know about our shader's attribute location for position. And there's a couple of ways that we could go about this. So the first way is that we could pass the shader into the load, which is it's far from ideal. So we don't want to pass our shader into the load method because we don't really want the sprite to know too much of anything about the shader, at least not at this point, not during loading. Our other option is to take a look at our actual shader itself, which right now is defined in engine, and have a look at our vertex shader source code here. And the location, as I mentioned before, this is actually going to be 0 because this is the first attribute in this, right? So if we had another attribute here that was called X or whatever, this would be 0, this would be 1. So what we're actually going to do in this case, because this particular sprite is going to be written with this shader in mind, because this is actually going to be pretty standard functionality for everything that we do, we're going to go ahead and set this location to 0 for this, instead of using it dynamically from the shader, because we don't really need to do that. The only reason that I did that was to sort of show how that works. All of our shaders are going to have a pretty standard set of attributes that they're going to use, and they're all going to be in the same order and typically have the same location. So for the purposes of this tutorial, what we're actually going to do is just set this to 0. And a lot of times you don't want to hard code things, but there are times where you have to sort of draw boundaries and figure out what is the most optimal way to actually set the engine up. Where do you want to draw the line as to how dynamic you want to be? And this is one of those cases where we don't want to be super dynamic with this. We always know that our position attribute is going to be the first in any shader that we use. So in this case, it's perfectly fine to just hard code it to 0. So that's what we're going to do. Now, back in the engine class, what we actually need to do, and again, this is temporary, but it will sort of show off the fact that our shader works as expected, is we're going to create another private variable, except this time it's going to be called sprite. And as you may have guessed, it's going to be of type sprite. Okay? And in our start method, before our loop actually begins, right where we used to have our create buffer method, I'm actually going to put a comment here for load. And underneath of that, we're going to say this.sprite equals new sprite, and we're just going to pass it a name of test. Doesn't really matter at this point what the name is. Alright, we're just going to use test. And if you recall, we have those default parameters width and height that are set to 10. So we're not actually going to pass those in. We're just going to accept those as is. And so you might be wondering, as far as this sprite goes, this width and height aren't actually used for anything. And that's absolutely correct. But we actually have to do a couple of other things before we can use those. So for right now, I'm actually going to stick with this as it is. And I'm going to go ahead and build this and run it. Oh dear. Looks like I've got... Oh, I know what the problem is. In Engine, within the loop, I forgot to draw it. So I need to say this dot sprite dot draw. And we don't need to actually hook up the update yet because it's not actually doing anything, but we will come back to that. Okay, so let me build this again. And refresh, force reload, and it's still not drawing. Okay. Cannot read property of bind of undefined. Let's see what it's talking about. This buffer bind. Oh, that's because it's going to be undefined, because we haven't actually called load. So that's an important detail. So here we need to actually say this dot sprite dot load. Let's build that again. And now we have our quad. So we haven't really accomplished too much in terms of visible progress here. But what we've done is we've decoupled a lot of our code and given ourselves a sort of platform to build off of for these sprites. So what we need to do next is we actually need to set up a couple more things in our shader to actually get this to run correctly. So what I mean by that is if we run this, and I brought this up once before, and we resize this window, you'll note that the size of the quad actually resizes with the window. And so we actually need to fix that problem, because that problem is actually going to give us a few more issues that are going to crop up and be a problem if we don't fix that now. Okay, so what we actually need to do is we need to create some math functions here, because there are some things that we actually need to tell WebGL as far as how to render this properly so that it shows up on the screen the correct way. And so under core, I'm actually going to add a new folder, and we're going to call this math. And underneath math, we are going to create a new TypeScript file, and that file is going to be called matrix 4x4 or 4x4. And we're going to do namespace TSE export class matrix 4x4. So what we are actually going to do is we are going to create a matrix class. And I don't really want to go into a lot of the details on how matrices work, because there are a lot of videos out there that explain that, and it can get really complicated. And so what I'm actually going to do is I'm going to go through a implementation that I've already done sort of in the past, and I'm going to sort of gloss over some of the details, because you could make an entire series of videos just talking about matrices and the math that's involved in them. So what we need to do is basically take the three-dimensional coordinates that are represented by our object in the world, and we need to transform them in such a way that we can then render that in 2D onto the screen. And there are a couple of methods of doing this, and since we're actually using a 2D engine, this is going to be far simpler than it would be for a 3D engine. But I'm going to talk in 3D here for a moment, because everything in WebGL is actually 3D. Again, I'm going to give a very quick overview on this. I really don't want to go too far into detail on this. There are tons of resources out there to read up on this, and I might make a supplemental video about this at a different time. But basically this image explains, for the most part, what a projection matrix does. And a projection matrix essentially takes the object, which is in 3D space, and from the position, from an eye position, which is another coordinate in the world, think of that as where the camera sits in the world. It figures out where these things are in 3D space, what you can see, what you can't see, what its rotation is, what its size is, how far away from the camera it is, and it figures out how to flatten that to 2 dimensions. This particular graphic illustrates a 3D projection matrix, or a perspective projection matrix, which is one of the most common projection matrices that you can have. It's not the only one, and it's probably not even the one we're going to wind up using, but the concept is the same. So what you have is you have 2 things that are called clipping planes. So you have a near clipping plane and a far clipping plane, which is represented by these 2 rectangles here. And what that means is anything that is closer to the eye than the clipping plane doesn't get rendered, because that means it's likely either behind you or too close to the camera to actually make sense when drawn to the screen. And the far clipping plane essentially does the opposite of that. So anything that's further beyond the far clipping plane in space is also not rendered. And that can help with performance and a lot of other things, and it can also keep you from rendering things that are so far away from you in space that it doesn't actually make sense to render them because they'd be tiny. The basic gist of it is anything that is between the near and the far clipping plane is what we're going to be rendering. You also have something called the view frustum, which is basically this shape here that's created around that. And so anything that extends beyond the x-axis or the y-axis extents of these 2 clipping planes is also not rendered. So obviously if it's outside your field of vision, you're not going to be rendering that thing. And so what we want to do is we want to represent this using matrices. And matrices look a little bit like this, only without the mathematical equations in here. These are for different types of matrices. So it's typically a set of numbers in one direction and a set of numbers in another direction. So a matrix is basically a 2-dimensional array. So you have columns and you have rows. And these things represent different aspects of 3-dimensional data. And so a projection matrix is actually represented, as the name implies, by a matrix. And so we actually need to create a matrix that represents this information in a form like this. So that's actually what we're going to do. And to do that, we actually need a structure so that we can provide operations against it and be able to use it with WebGL. And again, I realize that this is not a very in-depth conversation about matrices. I really don't want to go into that in this series. So if you don't want to read up on that any further and you're not interested in matrix math, don't feel like you have to learn it in order to proceed with this engine. You can just sort of use the code that I'm going to put here verbatim, and everything will work fine just as is. With all of that aside, what I want to do is I want to create a private field called data, and it's going to be an array of numbers. Okay, and I'm just going to set that to an empty array by default. And I also want to create a private constructor. And the reason the constructor is private is because I don't want to be able to say new matrix 4x4. And I'll make that clear in a moment as to why I'm going to be doing that. But for now, just create a private constructor. Okay, so inside the private constructor, what we want to do is we want to say this.data equals, and then open an array. And we want to create an array of 16 numbers. So those values are going to be 1, 0, 0, 0. And then in the next row, it's going to be 0, 1, 0, 0. And then in the third row, it's going to be 0, 0, 1, 0. And in the fourth, it's going to be 0, 0, 0, 1. And what this is called is an identity matrix. And an identity matrix is basically, you can think of it as your default matrix. all matrices are based off an identity matrix. So we want to actually create that as our default. And that's basically saying that these are ones diagonally across this. For now, what we're actually going to do is we're also going to provide a getter. So we're going to say public get data, and it's going to return a number array. And we want to return this data. Underscore data. There we go. And what we want to do now is we want to say public static identity. And that's going to return a matrix 4x4. And now we can just say return new matrix 4x4. And so instead of calling new matrix 4x4, which is the same thing as identity, a lot of math libraries will actually, or examples will actually refer to the identity matrix a lot. And so since that's what we're doing by default, we want a static method to create an identity matrix. So in order to actually create an identity matrix, you would just say matrix 4x4.identity, and that gives you an identity matrix. So we want to be able to do that statically from anywhere, not have to have an instance to worry about. We can just say matrix 4x4.identity, and it will return one of those for us. So the next thing I want to implement is a orthographic projection matrix. And an orthographic projection matrix basically doesn't provide any sort of perspective. It renders everything as if it's flat in space. So no matter how far away something is, it actually winds up being the same size. And you'll see this view actually a lot in 3D editors and wireframe views and things like that. And it allows you to see exactly where the points fall in the world on the X and Y axis, for example, without having to worry about any distortion or any skewing that's provided by perspective. So it's basically, it just flattens everything out. And since we're doing a 2D engine, that's the projection matrix we want to go with. So we're going to create a new public static, and we're going to call this OrthoGraphic. And it's going to take in several parameters. So it's going to take in left, it's going to take in right, which is also a number. It's going to take in bottom, which is a number. It's going to take in top, which is also a number. And it's going to take in a near clip, which is, surprise, surprise, a number. And a far clip, which is a number. Okay? And it's also going to return a matrix 4x4. So what these different properties are is you basically have to give it the bounds of the clipping planes, essentially. So if we refer back to our graphic here, it's these 4 lines that it's basically going to build. It's going to build the sides of the frustum that is going to make up our matrix. And for our purposes, that's going to wind up being the sides of the screen. So the left side of the screen, the right side of the screen, the bottom side of the screen, and the top side of the screen. And that's going to be the offset in number of pixels from those things. So left is almost always going to be 0, because it's 0 pixels from the left side of the screen. Right is going to be your resolution. So if this is a 1080p display, so from side to side there's 1920 pixels. So right in this case would be 1920. Bottom is going to be 0, because in WebGL and OpenGL, 0 is at the bottom. And then top is going to be 1080. And then our near clip is going to be something that's negative, because we don't really want to clip in front of us, and I'll go into that explanation in a bit. And then far clip is going to be some random number, probably 100 or something like that. So I hope that all makes sense. I'm going to actually move on just to keep this going. So what we actually need to do is we need to create a local variable that we call m for matrix, and we'll just say new matrix 4x4. which we can do that because our constructor is private, but we're within this class, so that's fine. And at the bottom we want to return m. Okay? So right now this doesn't really do anything, but we're actually going to fill out all of the different values of what m contains in it. And so we're going to have to do some math here to actually fill this thing out. So what we're going to do is we're going to create a new LR, and that's going to be a type number, and that's going to be 1.0 divided by, and then in parentheses we want to say left minus right. So this is basically just shorthand for left minus right. Okay, and then we want to say let bt number equals 1.0 divided by, as you might have guessed, bottom minus top. And then we also want to do the same thing with near and far. So we want to say number equals 1.0 divided by near clip minus far clip. Okay? And the reason I'm putting these as variables here is because we're actually going to use these things a few times. Okay, so the way that we're going to fill this out is element by element, right? So we're going to actually override what is stored in these individual elements where it's necessary. Otherwise, we're just going to use the default values. So in this case, we want to say m.data, underscore data, and we're going to set the first element in the array, which is index 0. So we're going to say the 0th index of this is going to be equal to negative 2.0 times LR. Okay? And we're actually going to leave the rest of these set to 0 for that particular row. So the next thing we're going to do is we're going to say m.data, and this time we actually want to access the 6th element, which is 0 indexed, so it's going to be 5. So that's going to be where this second one is right here. And we're going to set that to negative 2.0 times bt for bottom minus top. Okay, and the next thing we're going to do is m underscore data, and we're going to set the 11th or 10th index 10. We're going to set that to 2.0 times nf for near far. And we're going to leave the rest zeros. So the trickiness becomes in the last row. So this is the first row, this is the second row, this is the third row. Right, so we've replaced these 3 ones, and now we're going to replace all the elements except for the last one in this last row. So in order to do that, we're going to say m underscore data, and we're going to access the index 12, and we're going to set that equal to left plus top in parentheses times LR. And you can see here that we've now used this twice, which is why we saved it off here. Otherwise, we'd have to put this whole thing in here twice. And we're going to say m underscore data index 13 equals top plus bottom times bottom top. Next, we're going to say m underscore data, m dot underscore data, and we're going to access element 14, index 14, excuse me, and that's going to be far clip plus near clip, and that's going to be multiplied by nf. Okay? And so everything else here is going to be left to the default value. So we just need to override these particular elements. And you can already see why I don't want to go into a detailed explanation of this because explaining why all of this works would take quite a while. So again, I'm not going to go into detail on that. I just wanted to sort of reiterate that. Okay, so how are we going to wind up using this? What we're going to do is, in the engine, we are actually going to modify our shader a little bit. So what we want to do is we want to create a uniform. So we're going to add a new uniform. And this one is going to be of type mat4, which is matrix 4x4. And we want to call this projection. Oops, if I can spell that correctly. There we go. And this is actually where we're going to pass in our matrix that we're going to create here in a second. And what we want to do is we want to actually take our U projection, and we want to multiply it by our vector 4 that we create here. And so what this is going to do is it's going to transform our position into something that our screen actually understands. So in order to actually make this work, what we need to do is first I'm going to create temporarily here a private projection. We'll call it matrix 4x4. And in start, before we load the sprite anyways, we'll say that this dot projection equals matrix 4 dot orthographic. And so for the left, we're actually going to put 0, as I mentioned before. For the right, we're going to say GL dot, actually, we're going to say this dot canvas dot width, right? Because the canvas dot width is the width of our window, essentially. And then from there, we're going to say 0, and the top is then going to be set to this dot canvas dot height. And then the near clip, I'm actually going to set to -1.0. And that's because we don't want to set it to 0 or something in front of us, because if we recall, in our sprite class, we set the z index to 0. So if we were to set that to 0.1, this would be clipped because our near clipping plane would be on the other side of on the far side of our sprite, and so it wouldn't actually be rendered. So just to be safe, I'm going to set that to -1 so that we can capture that. And then I'm just going to set the far clip to, let's say, 100, just to be safe. We don't really need that much. 1.0 would probably work, but it's just to illustrate a point. Okay, so the next thing we need to do is we need to come down here to our set uniforms in our loop, and we need to say let projection position equal this shader get uniform location, similar to how we've done it before. And we want to say U projection. And then we want to say gl.uniform M4V. And what this actually means is it's going to take in an array, or a float 32 array, that's going to represent our matrix. So in this case, I need the WebGL uniform location first, which is our projection position. So I'm going to pass that in. And this is asking if we want to transpose it, which transposing is basically reversing the rows and columns, or swapping them out. We don't want to do that, so we want to pass false. And then we need a float 32 array. So for now, I'm just going to create a new float 32 array and say this dot projection dot data. Okay, and it's going to take that number array and convert it to a float32 array and pass it to the shader. And that should be all we need to do. So let's go ahead and run. Fresh. Oh dear. So it looks like... Oh, no, it did work. Okay. So this is a little bit hard to see, but if you look way down here at the bottom of the window, our quad is actually being rendered right there, and it's actually being rendered as like half a pixel. And so this is actually pretty much exactly what we expect, because our quad is actually very small now, because we're actually translating to the screen space. So before, the screen space was in those NDC coordinates, like I mentioned before. So if we look back at our paint, we had this whole -1, 1, -1, 1. So we had these normalized device coordinates, which is what the graphics card understands. But our projection matrix is actually now giving us different values to work with, right? So in this case, our quad wound up being very big because we're talking 0.5, which is halfway to 1 from 0, and so forth. But on our new scale, what we're actually winding up with is 0, 19, 20, excuse the terrible handwriting, I'm doing this with a mouse. And down here we have 0, and we have 10, 80 up here. Probably should have just typed that out, but you guys get the point. And so what that winds up resulting in is a very, very small quad being rendered down here somewhere. So with that, let's go ahead and fix that. Now, if you recall me mentioning before, our sprite is not actually making use of the width and height that are set. And that is because we're using the hard-coded values that are created right here on our vertices. So what we actually need to do here is convert these to use the width and the height instead. And so width is going to apply strictly to the x-axis, and that's going to be replacing all the 0.5s because that is the extent of it. So the zeros can remain as is, but now we can say this.width for our vertices, right? So we just replace everything on our x-axis, which is this first column here, with this.width. And the height is actually going to be represented in the same way on the y-axis. So we'll go ahead and swap all those out. And rebuild, and run again. And now, whoops, we have half of our triangle here. What happened? I think I messed something up in my... Let me just undo this. Oh, I replaced this 0. That shouldn't have been replaced. Okay, so basically with what we have here, we should have 3 widths and 3 zeros, and 3 heights and 3 zeros. Okay, and if I build that and run again, now we have our quad that's down here. So the thing that you'll notice is now this is sort of working, but not 100% yet. And that's because there's actually one more thing that needs to happen. Okay, so there's actually one more thing that we need to fix here to make our rectangle stop scaling with the window like that. And that's actually this GL viewport function here in resize. These parameters actually aren't correct for what we want. And so what we need to do is we need to set our viewport to -1, 1, 1, -1. And this is the NDC coordinates. So in other words, our projection matrix will actually map back to these. So we're telling WebGL this is what we want to use as our viewport, which is basically saying the max area of the screen. And so if we rebuild and run that, now we're actually getting our 10 by 10 pixel rectangle there. So great. So our canvas is this size, and our sprite is our 10 pixels. Okay, so let's go ahead and actually crank this up. We'll set this to 100. Okay. And go ahead and run this again. Right, so now when we resize the window, you can see that the aspect ratio of the square is maintained. So it doesn't deform when we resize the window, which is exactly what we want. And that's going to be the case for everything that we do here. And so we always want to make sure that we're maintaining this, and we're not scaling this in one direction or the other just because we've changed the window size. So this is what makes things a little bit more consistent, if you will. So the next thing that we need to set up is another matrix inside of our sprite. But before we do that, I actually want to set up another utility class that we're going to need. So in math, we want to say new TypeScript file. We want to say vector3. And a vector is a class which stores 3 values. So we want to say namespace TSE export class vector3. And again, I'm not going to go into a lot of detail on this. This is a lot simpler than the matrix 4x4 class, but for now I'm just going to keep this very simple, and I'm not going to go into much detail on this, but you'll sort of see how this comes together here in a moment. So in our vector3, we have 3 private members. So we have an underscore x, which is a number. We have a underscore y, which is a number. And we have a underscore z, which is a number. Right? So if you can imagine, this is going to store our positional data that we're going to pass into our shader, or use for some sort of mathematical computations or moving things around or whatnot. So we're going to wind up using this class a lot. So I think now is actually a good time to set it up and start using it. So to do this, we're going to create a public constructor, and we're going to take in an x number with a default of 0. We're going to take in a y number, default of 0, and a z number, default to 0. Okay, and then we're going to say this dot x equals x, this dot y equals y, this dot z equals z. And we're also going to create a couple of getters for this. So we're going to get x, oops, lowercase number, return this dot underscore x. And I'm going to do a public set x, and that's setters take in a value, whoops, number. They don't have a return type, and then we want to say this dot underscore x equals value. And later on it'll become clear as to why we need these. And what I'm going to do for the sake of brevity is I'm just going to copy and paste these and rename them. So, okay. And I'm also going to create a couple of utility methods here. So I'm going to create a public to array. and that's going to return a number array. And we want to return an array of this.x underscore x, this._y, this._z. And the reason I'm using the underscore ones or the private ones is so that we don't have to go through this accessor method to return it. It makes it a little bit faster when we call this method. Next thing I want to do is we want to create a public toFloat32 array. And as you guessed, that's going to return a float32 array. And we want to return a new float32 array. And we're just going to call this.toArray, since that will actually give us the number array that float32 array requires. So it's a nice, easy way. Now we can just say our vector3.toFloat32 array, and it's ready to use on our shaders. Nice and simple. I'm going to go ahead and comment these before I check them into GitHub. I'm not going to comment at things on screen anymore. It's just too time consuming. So I figured I'd point that out. Okay, so now that we have our vector3 class, we need to add some more stuff to this, but for right now, it's fine as is. So in our sprite, we're going to say, we're going to create a, let's create a public position type vector3, and we're going to default that to a new vector3. Okay, and that way we can just set this, and it's nice and simple to use. We're probably going to wind up changing this later on, but for now, that'll work. And what we need to do is in the engine, we actually need to add some data to our shader. So we actually need to add a new transform. And I'm just going to copy projection here and rename this to model. And what model is it represents position, rotation, and scale. So for now I'm only going to do position. And what this will allow us to do is change the position of our sprite in space. And all we have to do is set this model uniform to our position. So what it'll actually wind up doing is, you'll note that the type is matrix 4. So there's actually one more thing that we need to add in order to actually be able to pass in our position, because a vector 3 is not a matrix 4. We need to be able to convert that. So what we actually need to do is we actually need to create a new method in our vector 4, create a new public static, and we're going to call this translation. And translation is basically a matrix that holds data that represents movement of an object through space. So our position, it actually is the movement of our object from the origin, which is 0, 0, 0, to whatever the position of our object is in 3D space. So we need to represent that in a matrix. So to do that, we're going to create this static translation. It's going to take in a vector, let's call it position. And it's going to be a vector 3, and it's going to return a matrix 4x4. And we're going to follow the same pattern we did for OrthoGraphic, so we're going to say let m equals new matrix 4x4, and then return m. We're going to replace, or we're going to overwrite some of the values of the identity matrix, which is what we have here, with our positional data, so that we can actually represent this as a matrix. So in order to do that, what we need to do is we need to say m_data, and what we want to do is we want to access the 12th index, or the 12 index, which is the 13th element in the array, and we want to set that to position.x, right? So the 12th is here, so we have this, this, and this. These are the three that we want to replace, right? So x Y, and Z. And that's how you represent a translation in a matrix. So it's very simple. So we'll say m dot data 13 equals position dot y. Oops, m underscore data, and m underscore data 14 equals position dot z. And that's it. That's all we have to do to create a positional matrix or a translation matrix from a vector 3. So back in our engine, we're going to pass this in much the same way as we did for the projection. So we're going to say let model location equals this dot shader dot get uniform location u underscore model, which is what we called it down here. And then we're going to say GL uniform matrix for FB, and we're going to say model location, and then we're going to pass in false because we don't want to transpose it. And then we're going to say new float32 array this dot sprite dot whoops, I'm sorry, matrix matrix 4x4 dot translation this dot sprite dot position. Right, so we're going to take our position, create a translation matrix, and get the data from that, convert it to a float32 array, and then pass it into this guy. We're going to make some convenience methods to shorten some of this stuff up in a little bit, but I just want to get this up and running for now so that you guys can see how this stuff works. Okay, so the last thing that we need to do is we need to actually go into our shader and apply our model matrix. So we're just going to multiply that. And let's go ahead and build. And when we load, we see the exact same thing that we saw before, which is actually what we expect because we haven't actually moved the position of our sprite. So this is actually a good thing. That means what we have is working in theory. So the next thing we want to do here is after this .sprite.load, we want to say this .sprite.position, and let's go ahead and change the x. We'll set that to, I don't know, 200. Make it something really obvious. Right, so what we expect is that it'll move on the x-axis. So we'll build that, run it, and oh, that's interesting. Why has that? Aha! Okay. This actually gives me some insight into what's going on with some of the weirdness here. One moment. Okay, so I had a couple things that were messed up. The projection and the viewport were taking in the wrong values. And this was sort of what was screwing me up, and I didn't realize, and it took me a while to actually track this down. So the GL viewport should take in NDC coordinates. So as far as the device is concerned, or the window is concerned, it should be -1, 1, -1, 1. The projection matrix should take in, for the left, 0. The right should be the canvas width. The bottom should be 0, and the top should be canvas.height. And then I've put near and far both at -100 and 100, respectively. The other thing that I messed up was in matrix 4x4, I had this equation was wrong. So what I had in there was top in this position, and that's wrong. That was actually a typo. That should have been right. So it should be left plus right times LR. So when I run this, now everything looks good. So I apologize for that. sometimes when you're working with these things, it's easy to mix things up and sort of have to stop and debug and figure out what's happening and what went wrong. So, but now that I've got that figured out, let's move on. So what I want to do now is just re-enable our sprite.position.x. Sorry about that, I had some debug code in there. And now that we can see that that's actually been moved over by 200 pixels. So we know that that's actually working as expected now. So we have our sprite, we have the ability to move it around, and the ability to set colors on it, and so forth. And while this isn't a particularly robust class, I think that's where I'm actually going to end the video for now. The next video, we're actually going to do a little bit more cleanup, and then we're going to enable textures so that we can have textured sprites. Make things a lot more interesting. That way we can use an image and have a fancy looking sprite up on the screen with a texture on it that we can move around. So stay tuned for that next video. I hope you enjoyed, I hope you learned, and I'll see you guys next time.